Okay, welcome everybody. It's a pleasure to have Alessandro Monguzzi from University of Milano Bicocca. He will speak today on holomorphic function spaces on the Hartogs triangle.
Okay, so thank you, Marco. Thank you also to Nicole and Filippo for the opportunity to give a talk in this series of seminars. And so today I will talk about a project that actually is a work in progress, but already have some preliminary results, so I will talk about it. And so I will talk about holomorphic function spaces on the Artox triangle. So what is the Artox triangle? So the Artox triangle is this domain in C2. So it's given by the couple Z1, Z2, such that the mod of Z1 is controlled by the mod of Z2 and is controlled by 1. And is let's say, a famous domain because it's a source of many pathological facts in complex analysis. So what I mean by this, for instance, it is a bounded pseudo-convex domain with the non-trivial Nebenhullen, which means that the closure of H cannot be written like as the intersection of some domain omega k, where each omega k is a pseudo-convex domain. So this is a picture of the Artox triangle, where on the x-axis you have the mod of Z1, and on the y-axis you have the mod of Z2. So the name triangle is obvious. And so now, I mean, it's not hard to see that it has non-trivial Nebenhullen. It is quite a well-known fact, but it's quite simple to see it. So I will spend a couple of minutes showing this fact here. So let's take an egg brood of the Artox triangle. So here I just drew a slightly bigger triangle, but as soon as we take an egg brood of the closure of H, we can consider this L-shaped domain here, this is in blue. So here you have to think that this side here is of length epsilon, actually. So this L-shaped domain actually is something like this. So this is rotated, and here, so this L-shaped domain here is like fat, and it is something like this, where here this side goes from 1/2 to 1 and from 1/2 to 1. So now, if you consider any holomorphic function on this domain, F, then we can define another function f hat of Z1, Z2 as follows. Here, we consider just the Cauchy integral of the function in the second variable. Here we have f of Z1 and Greek zeta. And here we have the Cauchy kernel in zeta minus Z2. And we are integrating on the circle of radius 2/3. But so we are with the Greek z, we are somewhere here. But when we are here, the Z1 belongs to the unique disk. So actually, this f function f hat is actually a well-defined holomorphic function on the polydisk D01 times D0 2/3. And but of course, the f hat and the original function f, they do coincide on the intersection of these two domains here. And so actually, we extended we can extend any holomorphic function f on this L-shaped domain to the whole polydisk D01 times D01. So what about the triangle? This means that if we consider a pseudo-convex domain that contains the closure of the Artox triangle, then this pseudo-convex domain contains an L-shaped domain like this. And so we can extend function to the whole polydisk. So any pseudo-convex domain actually containing the closure of the Artox triangle has to contain as well the whole polydisk D01, D01. So we cannot achieve anything like this. So with this, I mean that the Artox triangle is a source. This is an example of what I call pathological behavior or pathological effects on the Artox triangle. So quite recently, let's say since 2015, more or less, several people got interested in studying the mapping properties of the Bergman projection and some related problems on the Artox triangle and certain generalization of this domain. So I now just recall you that the Bergman projection is is defined as follows. Given a domain omega in Cn, the Bergman projection is just the orthogonal projection from the L2 space on the domain onto the closed subspace of the square integrable function, which are also holomorphic, which I denote by A2, and this is the Bergman space. And the Bergman projection, so it's just this projection here. And so this is an incomplete list of people that have been working on Bergman projection on the Artox triangle and related domains. For example, we have Chakrabarty, Chen, Needham, Wu, Krantz, McNeil, Mechisho, Khan, Wick, Zaitunku, Wan, and some other people. And just let's see a result in this context on the Artox triangle. So here I recall this theorem due to Needham and McNeil. They consider, they have a parameter gamma greater than 0, and they consider these domains that they call generalized Artox triangle, which is defined as follows. H of gamma, we have the pair Z1, Z2 in C2, such that the mod of Z1 to the power gamma is controlled by the mod of Z2 controlled by 1. And so the classical triangle is, of course, corresponds to the case gamma equal 1. And what did they prove? They proved that if gamma is a rational number, m over n, and when m and n do not share divisor, then the Bergman projection extends to a boundary operator on LP if and only if P belongs to this bounded interval here, which explicitly depends on m and n on gamma. But if you take a gamma which is an irrational number, they prove actually that the Bergman projection is a bounded operator only on the trivial case of P equal 2. Because being a projection is always bounded on P equal 2, and if gamma is irrational, is the only case where P gamma is bounded. So this is another, let's say, pathological fact about the Artox triangle. So other people studied the following fact. Let's see just a few facts that people studied on this setting. For instance, Chen studied the weighted Bergman projection, where the Bergman spaces is defined with respect to a weighted measure, and the weight on the measure is the following one. It's just the mod of Z2 to the power nu, where nu is a real parameter. So, of course, this weight here interacts with the origin, which, sorry, I didn't tell you, but you can see it here. Also for gamma equal 1, but also for every gamma, actually, the origin is the most pathological point of the boundary of this domain, because you cannot even represent locally the domain there with a continuous function, for instance. So this weight here interacts with the origin, of course, and so it does play a role. Then Chen, but jointly with Zaitunku in 2017, they studied weighted Bergman projection, but this time the weight is an exponential weight, which is this one. So again, when we go close to the origin, this weight here goes to 0 very fast. And Chakrabarty, Needham, and McNeil, for instance, in 2019, they actually studied duality and approximation for Bergman spaces on generalized Artox triangle when gamma is greater than 1. And for instance, they explicitly describe the dual space of AP. So AP prime, this is this dual space of AP, and in general, it does not coincide with the AP prime, the expected result, and this is also due to the fact that the Bergman projection is not bounded, and but they explicitly describe it, and they also study, when I say approximation, the density, for instance, of H2 intersection with AP in AP, and problems like that. Then Khan, Liu, and Tuk study, for instance, in 2019, the Bergman Toeplitz operators on generalized Artox triangles, whereas Wu and Wick recently, they study endpoint and weighted estimates for the Bergman projection on the classical triangle, and they do that by using techniques of dyadic harmonic analysis. So quite a few people have been working on Bergman projection related problem. But my question now is, okay, but what about other holomorphic function spaces on the triangle H? So that maybe you can study and so understand or find other pathological behaviors, and so maybe find some hints for more general results. So the problem is that, first problem is that, for instance, the definition of classical spaces such as the Hardy or the Dirichlet space on this domain is not canonical. They are not trivially defined as the Bergman space. So in the rest of my talk, I will spend my time actually defining a family of function spaces on the triangle, which is in some sense an analogous of a well-known space of holomorphic function on the unit disk, which is known also with the name of Hardy, Bessel, or Sobolev spaces. And with this, I mean the family of holomorphic function spaces associated to the one-parameter family, to this one-parameter family of kernels. So here we have k nu z of w equal 1 over 1 minus z w bar to the power 2 plus nu, where nu is a parameter greater than minus 2 and zw belongs to the unit disk. So this is a well-known family of kernels. In fact, we recognize the weighted Bergman spaces on the unit disk when nu is greater than minus 1. The Hardy space is corresponds to the case of nu equals minus 1. The weighted Dirichlet space is when nu is between minus 2 and minus 1. And actually, we also have the Dirichlet space, which is the limit case for nu equals minus 2. And so the kernel is not this one, but it becomes a logarithm. So, so now I'm going to describe that I introduce and describe a family of function spaces on the triangle, which is analogous to this one. So what about weighted Bergman spaces? So we consider we have the parameter nu greater than minus 1, and we define weighted Bergman spaces as follows. We just consider the holomorphic function of the triangle such that are square integrable with respect to this weighted measure. So dz is the Lebesgue measure, and here we have a power of this kernel here, and this is just the kernel, the Bergman kernel of the unweighted Bergman space A2. So the case of nu equals 0. So we take this kernel, the Bergman kernel of the unweighted Bergman space, we restrict it to the diagonal, we consider this power here. So why this weight here? Because actually this behaves like it is comparable with the distance of the point Z to the boundary, and it will interact, for instance, with the origin, but we will see later in greater details. And so, and here chi nu, this is actually also the norm on the space, and c nu here is just a constant such that the weighted measure of the triangle is equals 1 over c nu here. So here gives you 1 here. So, okay. What about this Bergman kernel on the weighted case? Can we find this kernel? So the answer is yes. It's quite easy to find it because, okay, in general, if you have H, a reproducing kernel in the space, an orthonormal basis, phi n, then the reproducing kernel of the space, K of H in ZW, is given by this sum here, phi n of Z and phi n bar of W. So for the Artox triangle, for the Bergman space on H, we have that an orthogonal basis is given by the monomial Z1 to the J, Z2 to the K, with this restriction on the index. So we have J greater or equal 0 and J plus K plus 1 greater or equal 0. And then we can normalize, of course, these monomials, and we end up with the sum here for the kernel. But then this sum here is explicitly computed easily, and we end up with this kernel here. So we have Z2 W2 bar over, okay, the constants 2 times Z2 W2 bar minus Z1 W1 bar to the square, and times 1 minus Z2 W2 bar to the square. Okay, so of course, when we restrict this kernel to the diagonal, so when Z is equal W, this is positive. And in conclusion, we have that F belongs to the weighted Bergman space A2 nu if and only if it is square integrable with respect to the measure d mu nu, where d mu nu is this weighted measure here. So C, some normalization constant, and then we have Z2 to the nu time, and so this factor here interacts with the origin, which is the, as I said, the most pathological point of the boundary of our domain. Then we have 1 minus the mod of Z1 over Z2 to the square to the nu, and 1 minus the mod square of Z2 to the nu. Okay, so this is the measure we consider, and now I just want to point out that if you write the weighted Bergman norm of a function f with respect to is a Lorentz series, so a, j, k are the coefficient of the Lorentz series of the function f, you end up with something like this. So we have this norm here, and here I just want to point out that this power series expansion is actually, let's say, is well defined when the parameter nu is actually greater than -2. For instance, here we have gamma of j plus nu plus 2, and we can take and j is starts from 0. So we can consider nu greater than -2. But when I define the Bergman with the weighted Bergman spaces, I said that the nu is actually greater than -1. And this is because actually we can define the weighted Bergman spaces for any parameter nu, but they are meaningful only for nu greater than -1. Because otherwise, so when nu is equal or less than -1, these spaces are actually empty. Okay, so another remark, sorry, here just also want to say that, as I said before, Chen studied weighted Bergman spaces where as a weight he only considered this factor here. So my case is different than Chen case because we have also these two extra factors here. And in fact, in Chen cases, the weighted Bergman spaces are meaningful for any real number nu, whereas for us, they are meaningful only when nu is greater than -1. So another remark is that the Artox triangle is actually biolomorphically equivalent to this product domain, which is the unit disk times the punctured unit disk. So this star is the unit disk without the origin. So this function phi here is the biolomorphism. So if we have W1, W2 on this product domain, then W1 times W2, comma W2 is the point, the corresponding point on the triangle. So clearly this map here, so the map that to F associated the Jacobian of phi times the composition of F with phi is a surjective isometry from the weighted Bergman space on H onto a weighted Bergman space on D times D star. And which, what is this weighted Bergman space here on this product domain? Is the space of holomorphic function with respect to this L2 norm. So we have this weight here. In particular, here we have, so here you can recognize, in these two factors here, you recognize the, the standard weight for the polydisk, but we have this extra factor here that, of course, takes care of the fact that on the second variable, we work on the punctured unit disk. So, okay. Okay. Of course, the space, the weighted Bergman space I defined are, of course, a reproducing kernel Hilbert space. An orthonormal base is given by the normalized monomial Z1 to the J, Z2 to the K, where we have this restriction on the parameters. So we have J greater or equal 0, and then we have that J plus K plus nu over 2 plus 2 is strictly greater than 0. So this is an orthonormal basis for our spaces, and so we can compute the reproducing kernel of these spaces, and they are given by these the reproducing kernel are as follows. So we have this factor here, this factor here, and this sum. But actually, we are quite lucky because it's probably a coincidence, but it's quite nice because if you take a closer look to this sum here, we conclude something more actually, that the reproducing kernel can be written as follows. So we have a constant here. Then here we have Z2 W2 bar to the power -1 minus this is the ceiling function on nu over 2. So this is the smallest integer greater than nu over 2. Then here we have 1 minus let's say the diagonal term Z1 W1 bar over Z2 W2 bar to the power 2 plus nu. And this half here, which depends on these three on nu and zt, and it is a function in Z2 W2 bar, is the hypergeometric function, which is defined as follows. We have alpha, beta, gamma that are complex parameters, but we require that gamma is not a non-positive integer because if otherwise not well defined. and it is defined by this power series when Z belongs to the unit disk. So for us, here we have Z2W2 bar that, of course, it is in the unit disk. It is well defined, and as it was the case for the weighted Bergman norm, here I also, okay, no, sorry, another check here. Before I want to say the following, that if, for instance, if nu is an even integer, nu equal to n, then the hypergeometric function is equal to 1 over 1 minus Z2 W2 bar to the power 2n plus 2, where 2n is our parameter node. So actually we have something like this for any value of the parameter node, because so this is the kernel, I just brought it again. If you consider from standard estimates on the hypergeometric function, we always have that the absolute value of our kernel is bounded by this function here. So here we have is just the mod of this factor here. This second factor here is just the mod of this factor of this term here. But we can always bound the hypergeometric function with 1 minus Z2 W2 bar to the power minus nu plus 2. Okay, so also another thing I want to say that I was saying before is that we are working with Bergman spaces that are well defined, or that are meaningful actually only for nu greater than -1, but the kernel, as well as it was the case for the power series expansion, let's say, of the weighted Bergman norm, the kernel is actually well defined whenever nu is greater than -2. And you can see it here. For instance, this was the gamma parameter in the definition of the geometric function, hypergeometric function. So when nu goes to -2, this goes to 0, and so this is not well defined anymore. And again, we will come back later to this. So now we have weighted Bergman kernel, so we can study the weighted Bergman spaces, so we can study the weighted Bergman projection, and we can study, for instance, the LFP mapping properties of the weighted Bergman projection. So in this case, the weighted Bergman projection is the following operator: is we are given a function f, we are integrating the function f against the kernel with respect to our weighted measure d mu nu. So this is the orthogonal projection from the L2 space, the weighted L2 space, L2 nu, where denote the weighted L2 space with respect to this measure here, d mu, onto the weighted Bergman space. So what about the LP mapping properties? We have the following results: that if the weighted Bergman projection extends to a bounded operator on LP if and only if P belongs to this bounded interval here. So actually, the proof of this result, as in the case of for instance, Edom and McNeil result, it follows from, let's say, standard and classical arguments. You have to be careful with the computation, of course, but let's say that the main, once you have the kernel of the space, the main tools are classical ones. So now I will say a few words about the proof. So, for instance, now we consider the following function to prove the unboundedness of the projection. F of Z1, Z2 equals Z2 bar to the power 1 plus the ceiling function on order 2. So this function easily belongs to any weighted LP for all P between 1 and infinity. And I mean, using the resonance of the kernel, we easily compute its projection. And up to a constant is given by the projection of this function f here is just the monomial z2 to the power -1 minus the ceiling function of nu over 2. And so now the LP norm of this function here is easily computed, and we conclude that the weighted Bergman projection cannot be bounded on LP if P is greater or equal this quantity here, which is the same quantity that appears here. So Then by duality, by standard duality argument and the self-adjointness of the projection, we conclude that actually P cannot be, the Bergman projection cannot be bounded if P does not belong to this interval here. Okay. So to prove the other direction, so I mean, this was quite easy because we easily found a function that provide a counterexample to the LP, to the LP boundedness. Then to prove the converse, the converse, we consider we want to use the Schur lemma, and which gives you the Schur test, Schur lemma that gives you a test to prove the LP boundedness of integral operators when the kernel is positive. So we do not consider our original operator, but we consider the integral operator whose kernel is the modulus, the absolute value of our weighted Bergman kernel, and we study the boundedness of this operator, of the operator that have this kernel. Then from this it will follow easily the boundedness of our original operator. So to apply Schur lemma, we need a positive function f that satisfies this estimate here. So we are integrating the power p of the function f against our positive kernel. Here we are integrating w, and the kernel is in z and w. And we want this quantity to be bounded by the p power of the function f in z, z1, z2. And we also want the same estimates for where we take p prime, the conjugate index of p, instead of p prime. So we consider the following test function here. So we have a 1 minus the mod squared of z1 over z2 to the power minus alpha. Then we have 1 minus the mod square of z2 to the power minus beta, and z2 to the power minus gamma. So somehow this function here is, I mean, it interacts well with the density of the measure here we are considering here. Then we use some Forelli-Rudin estimates that are very classical, and we actually conclude that we have this estimate here for p and p prime if these two sets of conditions are satisfied. That I'm not going to read this condition, but you want this condition to be satisfied simultaneously, and you end up, you actually deduce that this happens exactly when the p belongs to the interval we are interested in. And so this actually concludes the proof. Okay, so we defined the weighted Bergman space on the Hartogs triangle, and we studied the p mapping properties of these of the weighted Bergman projection, and now we want to introduce some new spaces. So what about an RD space on the Hartogs triangle? So, okay, let's just recall you the definition of RD space when we have a domain omega, which is defined by the defining function rho. So it's given by the z, such that rho of z is negative, and we assume that omega is moot as bounded. Then, to define the RD space H2 of omega, we consider a family of approximating domains omega epsilon, defined as follows. So are the set of points z such that rho of z is smaller than minus epsilon. D sigma epsilon is the induced surface measure on the boundary of this domain omega epsilon. We take the L2 norm here, and we take the supremum over the parameter epsilon. So so this definition is not suitable for the Hartogs triangle case because of our singularity at the origin principle. So we have to find another way to define a space that we're going to call it RD space, and somehow justify the name of RD space, and study this space. So in particular, in our case, what I want to do is to define a space that I will call the RD space on H, which is just a possibility for a RD space on this setting. I want this space to be the limit of the weighted Bergman spaces A to nu when the parameter nu goes to -1. So in particular, I have a family of kernel K nu, that then when nu is greater than -1, they are the kernels of the weighted Bergman spaces. And I want the case -1. I want the Hardy space to be the holomorphic function space that has the reproducing kernel k-1, which is the following one. If you take our family of kernel and just take nu equal -1, you end up with this kernel here. So we have actually we have a prescribed kernel, and we want to find that we know is a reproducing kernel, and we want to, I mean, we know it's okay. We want the holomorphic function space that has the given kernel as a reproducing kernel, and so we define. We end up with this space here. We consider the space of holomorphic function on the Artox triangle. We still consider a family of approximating domains, HST, which are defined as follows. We have the mod of Z1 over S, which is smaller than the mod of Z2 smaller than T. So these domains are all strictly contained on the Artox triangle. So dB of HST is the distinguished boundary of HST, which is obtained when here, instead of these inequalities, we have equalities. So we have here, equalities here. And actually, so it is immediate to see that actually the distinguished boundary of these domains can be identified with the two-dimensional torus. And then d sigma st is the induced surface, is the surface measure, the induced surface measure on the distinguished boundary of these domains. So we consider, and then we take the supremum of we consider L2 norm here, and this L2 norm here, and we take the supremum on S and T for S and T in 0, 1 times 0, 1. So, so this space is the one we were looking for, because we have that the monomial Z1, J, Z2 to the K are an orthonormal basis for our space when with these restrictions on J and K. So J is greater or equal 0, and J plus K plus 1 is greater or equal 0. This space, this Hardy space, is contained in all the weighted Bergman spaces I defined before, and the H2 norm of F is equal to the limit to the weighted Bergman norm of the function F. And the reproducing kernel space, the reproducing kernel of is a reproducing kernel Hilbert space, and the reproducing kernel is the one is k-1, the kernel we wished. Okay, so now a few remarks on this definition. So, for instance, the pathological point, so the origin, which is let's say the pathological points of the topological boundary of the Artox triangle angle actually belongs to the topological boundary of all the approximating domains we consider. So then, why we consider this family of approximating domains? That depends. For instance, this family of approximating domains depends on two parameters. We could have considered one parameter family of approximating domains defined like this. So here we have the mod of Z1 over T, which is controlled by the mod of Z2 controlled by T. But but we could also have used other family of approximating domains. I mean, we would end up with different, let's say, Hardy spaces. And so, I mean, this is a point of interest, actually. What is a meaning? How can we define meaningful spaces on such a domain? What are the differences between the spaces? So this is actually something that I'd like to investigate more. But on this very same topic, actually, very recently, a preprint was appeared on the archive by Gallagher, Gupta, Lanzani, Vivas. And they were actually studying how to define meaningful Hardy spaces on singular domain, and they actually work. They work actually also in a different but also more general setting than mine. But then actually, as they say in the preprint, they also saw what I was doing, because my preprint on the Artox triangle was out. So they also then investigated the Artox triangle case, and so they actually proved something related to how to define suitable Hardy spaces on singular domain and on the Artox triangle as well. And they also consider the space I defined actually. So for us, just let's say that for me at the moment, the goal here was we have a family of kernels. We have a prescribed kernel. We wanted to find the space that has that prescribed kernel, and the space I defined is actually the space I was looking for. Okay, so now that we have let's say a Hardy space on the Artox triangle, we can study the Ziggo projection. So our Hardy space can actually be identified with this space on the distinguished boundary of the domain. So H2 of DDH is the space of function that look like this. Here we have this restriction on J and K, and where the coefficient are here in L2. So the Ziggo projection is the projection from the L2 space on the torus, on the two-dimensional torus, which can be identified with this distinguished boundary, onto our space H2 here, and it's simply defined like this. Okay, we also have an integral representation in terms of the reproducing kernel of our Hardy space, but I did not include it here the formula. And unlike the weighted Bergman projection case, we actually, the weighted Bergman projection, we have that the Ziggo projection actually extends to a bounded operator for an EP between 1 and infinity. So the proof is very simple actually now, because we can identify the distinguished boundary of H with the two-dimensional torus. And so the boundariness of the Ziggo projection simply follows from the boundariness of the Fourier multiplier operator associated to this multiplier here. So this is just the multiplier, let's say, as more or less the multiplier of two Hilbert transform. So, I mean, I'm sure that everybody knows in the audience, but just to recall you the definition, what is a Fourier multiplier operator on two-dimensional torus? Given a function f, we associate an L2 function f on the two-dimensional torus. We associate this Fourier series here. So f(f) is the Fourier coefficient of the function f, and the mjk is the multiplier, is a bounded sequence, and in our case, mjk is given by this. So here, I do not go into details, but it really follows from very classical results. So we defined, weighted Bergman spaces, and we studied the Bergman projection. We defined a Hardy space, let's say, and we studied its associated Ziggo projection. What about weighted Dirichlet spaces? So now I want to enlarge our family of spaces, because so we have our family of kernels, which is the following, which is this one, and we define. So we characterized all the spaces for the value nu greater or equals -1, and now we focus on the other range on when nu is equals or greater than -2 and smaller than -1. So now let us go back for a moment to the unit disk. So on the unit disk, the Hardy Basel Sobolev spaces that I mentioned at the beginning of my talk, of my presentation, are also characterized by this semion here. So here, what we are on the unit disk, we have let's say the standard weight on the unit disk, the standard weighted measure on the unit disk. So this is actually the restriction of the Bergman kernel of the unit disk to the power -nu/2. Then here we have a derivative of the function f. R of f is the radial derivative of the function f, which is defined as follows here. And then we have this extra factor, this extra weighted factor here. So when nu is greater than -1, actually this quantity here is equivalent to the classical weight, to the standard weight and classical weighted Bergman norm on the unit disk. But for nu between -2 and -1, this actually semi-norm actually identifies and defines the weighted Dirichlet spaces on the unit disk. And for nu equals -2, we have the Dirichlet space. Particular for nu equals -2, here the measure is the Möbius invariant measure when nu equals -2, and actually this weight here cancel out with this weight here, And so we only end up in the Dirichlet case with the L2 norm of the derivative of the function here. So now I want to prove something similar on the Hartogs triangle, and use something like that to define weighted Dirichlet spaces and the Dirichlet space on the Hartogs triangle. So we have the following result. If we consider a generic holomorphic function on the Hartogs triangle, which has this Laurent series expansion, and we define the following function. F1 of Z1, Z2, we have this sum here. We have J times J plus K, AJK, Z1 to the J, Z2 to the K minus 1 here. And we are summing when from J that goes from 1 to infinity, and when K is not equal minus J. So here, if F is this one, F1, it's a sort of derivative. It's some derivatives. We apply some differential operator to the function F. F2, now I will say something more about this later. F2 actually is like F1, but it is the case when J is equal to 0. In fact, here we only have the coefficient A0K, and we are summing on K when K is not equal to 0. And we have K is 0K, Z2 to the K minus 1. So is actually like F1, man, is the case J equals 0. And finally, the last case is F3, which is the case when we are summing on J, but K is equal minus J. And so here we have the coefficient AJ minus J, and then we have J times the coefficient AJ minus J, Z1 to the J, Z2 to the minus J minus 1. So these are all, let's say, derivatives of the function f. And we prove that actually f belongs to the weighted Bergman space A2 nu, when nu is greater than minus 1, if and only if this quantity here is finite for all these derivatives of the function f. So here we have our weighted measure, this extra weight here, and these derivatives f1, f2, f3 of the function f. So this is really the analog of the result that I showed you before on the unit disk, because we have the weighted measure, an extra weight here, and the derivative of the function. So it was like this: the weighted measure, an extra weight here, and the derivative of the function. The radial derivative of the function here, instead of the radial derivative, we have this, let's say, this check more than one term. So, okay. So, but the point is that we can actually now use this quantity here to define, to define weighted Dirichlet spaces, and that's what we will do. But before doing that, just a remark, I want to tell you that, so recall that H is actually biholomorphically equivalent to this product domain, D times D star. And consider this isometry here, the one that we saw a few slides ago. So if we apply this isometry to our derivatives f1, f2, f3, we end up with something like this. So f1 tilde, we applied this isometry here to the derivative f1 of the function on the Hartogs triangle, and we obtain something like this. So we have jk, aj, the coefficient is ajk minus j, when this is the coefficient of the function on the Hartogs triangle, and w1j, w2k. So here, we have something like the radial derivatives on both the first and the second variable. For f2, we end up with the radial derivatives on we have a function that only depends on w on the second variable, and we have the radial derivative on the second variable. Whereas for the last term f3, we have the function that depends on the first on the first variable, and we have a radial derivative here. And so we have the analogous result that f belongs to the weighted RD space on d times d star if and only if this quantity here is finite for all these derivatives, f phi tilde, let's say, where d mu tilde is the weighted measure on our product domain d times d star. Okay, so so we now define the Dirichlet space follows as the space of holomorphic function on the triangle, such that this quantity here is found with this norm. Here we have, these are the semi-norm of our derivatives, and this is, okay, this, let's say, is the value of the function f at the origin. I mean, it's not truly the origin, but we need this term here to so that this is a norm. And okay, once we have this, we have defined the space, we can actually find a different inner product on this weighted Dirichlet space, such that, which I denote by the bracket sub d nu, such that the weighted Dirichlet space with respect to the norm induced by this Reproducing kernel is their space, and the kernel is the one we were looking for. So is a kernel of our family for between -2 and -1. So the proof actually, once we define the space with this norm here, then we consider an holomorphic function f in this space, and any holomorphic function f in this space turns out to be of this form. We find the basis of these spaces here, so we find this restriction on the monomial z1 j z2k. We have j that goes from 0 to infinity, and this is written like this, but this is the very same condition that we had on the weighted Bergman spaces. So j plus k plus nu over 2 plus 2 strictly greater than 0. And so actually, what is the inner product that we define now is the following one. So this is the very, let's say, is the inner product that this is the coefficient, the very same coefficient that we saw in the, let's say, power series expansion of the norm of a function in the weighted Bergman space. But this norm here turned out to be equivalent to the norm we used to define the space. And with respect to this norm, the reproducing kernel in the space is, of course, the one we were looking for. We needed although to define the spaces with respect to the norm star, because we needed we needed a condition on a generic holomorphic function f to impose a condition on a generic holomorphic function f to belongs to our spaces here. We need to find somehow this condition on j and k. Once we know this condition, we can define this inner product here and conclude. So finally, I define also the limit k for the space for the parameter for the value nu equal -2, which is the a candidate Dirichlet space. So again, here we use this norm here. So these are the semi-norm of the derivatives of the function f that I define, but when the parameter is equal to -2. And here I want to note to emphasize the fact that the weight in the density of our norm, so the weight in our measure actually cancel out this extra factor here, and here we only end up with the L2 norm of our derivatives. Okay, and moreover, also the measure for, in this case, d mu -2 in the definition of the Dirichlet space is invariant for the automorphism of the Artox triangle. So as in the case of the unit disk, we had the Möbius invariant measure. So here we have this measure which is invariant for the automorphism of the Artox triangle. And so this is easily seen because, the automorphism of the Artox triangle are completely described as follows. We have psi z1 of z2 equals z1 tilde z2 tilde, where z1 tilde is equal z2 times phi of z1 over z2, where phi is an automorphism of the unit disk. And we are in the triangle, so z1 over z2 always belong to the unit disk. And on the second variable, we only have a rotation. So z2 tilde is cz2, where c is a complex number of modulus 1. So this is the measure. In the case -2, we only have the kernel restricted to the diagonal, and explicitly is given like this. So to see that the measure is invariant for the automorphism, we just consider the composition of the kernel with an automorphism, and in the second variable nothing happens because it's just a rotation, and here we always have the absolute value. So what I'm saying is the following: to show that the measure is invariant for the automorphism, we just have to check this identity. So k in psi z times the modulus square of the Jacobian psi prime z in this z is equal k z in this z. But this holds on if and only if these other identities satisfied here. So 1 minus, here I forgot a square, sorry. The mod of phi of z1 over z2 to the -2, here this Jacobian of phi. But this follows immediately because now this follows from the invariance of this measure here with respect to the automorphism of the unit disk. Okay. And so also in the Dirichlet space case, we have now, we define the space where we can consider a different inner product such that the space with respect to the norm induced by this new inner product is a reproducing kernel space whose kernel is given by this. Is the following one, where logarithm terms appear. So we have 1 over z1 omega 2 bar, and then we have the product of this logarithm here. So this is okay. This is the log of this diagonal term and the log of this term here. So the proof, again, we use the norm star to find out that any function f is to find out to actually find a basis for our spaces. Once we have this restriction on the index j and k, we define the inner product in this way, which again corresponds somehow to is the limit case for node that goes to -2 of our family of kernels. So what's next? Actually, so far this is what I wanted to say. I defined this function of this family of holomorphic function spaces on the triangle. And so now actually I want to investigate this space and see if something interesting or pathological comes out to justify actually the introduction of these spaces. But this is actually work in progress, so I have nothing really more to say, and I thank you for your attention.
Thank you, Alessandro. And I wanted to ask if there are questions.
I have a question.
Go ahead, Fulvio.
Can you go below -2?
It is a natural question, but right now I really didn't think about it. Mm-hmm. But of course, I mean, if you look at our kernel, you can actually, you have an hypergeometric function that you can actually extend the hypergeometric function whenever the parameter is not a non-negative integer. So clearly the question is meaningful, but honestly, that I didn't really think about it. You only have to keep the negative well-defined. Mm-hmm. So, but I don't know.
Okay. I was asking if there was an obstruction that you had found. Okay.
Are there any other questions?
I didn't really think about it. I mean, it's something that I might have to do, but I do.
But, I mean, is there a kind of Hardy operator that let you shift the parameter nu back and forth by integers, maybe, and
yeah,
and then reproduce the situation further and further.
Yeah, I understand what you're saying. Yeah, I have to think about it, but I understand.
I'm talking by analogy with I don't know, the disk.
Yeah, sure. Yeah, actually, I expected that it's gonna work probably because of the biomorphism with with the disk and the star. You only have to. I mean, you can always exploit this biomorphism, but of course, then the LP mapping properties of the projection are completely different. So pathological things happen. So, but of course, you can think like that. Thank you.
Okay, sorry, didn't want to interrupt before. Are there other questions?
I have two questions. Well, one I think maybe to be okay, it would be interesting to study boundary values for these spaces to see boundary values and the regions on which the cones on which you can approach the approach regions to get to the boundary for some of these different spaces, like between Hardy and Dirichlet and everything in the middle. And the other one is do you know some of these spaces?
No.
Yeah, if they have this peak property or maybe or.
So about the big property, I don't know. That's my answer. About the boundary values, I mean, you're right. It's really interesting to study the boundary values of this function also because I don't really know what it means to study boundary values when you go to the pathological point to the origin.
Right, that would be the interesting.
I mean, that's all. I mean, that's the interesting situation. But it's something that for sure it's worth investigating. Then I was thinking about studying the Carlson measure on the Dirichlet spaces.
Right, yeah, you put some trace.
Also, I mean, exploiting also, you know, the actually your work on the Carlson measure on the by disk.
Yeah,
So
I
because
hope here it's easier.
yeah, I mean, I don't know. You know, the triangle is biolomorphically equivalent to d times d star. So maybe some of your work on the product situation is worth. I mean, to take a look at it for sure. But it's really work in progress.
That would be really interesting.
Are other questions? I have one. You talked. I don't remember what you said about the regularity of the Bergman projection for the Hartogs triangle, because you said that Hedholm and McNeil had a theorem of irregularity somewhat. I mean, so the LP bounds for the Bergman projection were only valid for some small interval, and instead you found that for the particular for the Hardy space projection it is regular for all p's between 1 and infinity.
Yeah.
So I was wondering how the two things are connected, and how, in case you would explain the fact that in the limit case you recover the regularity for all p's.
Okay, yeah, that's something I actually thought about, but I mean, in for let's just say, I don't know if where is
because well, for one thing, they didn't consider the powers of the Bergman kernel along the diagonal, if I'm correct.
Yeah, no, Hedholm and McNeil, they only consider they are working on a different domain.
Oh, okay.
They work on this domain here. You can still see my screen, right?
Yeah, yes.
They work on, so here they have this power gamma here.
Okay.
So the triangle, the classical one is when gamma is equal 1. And
so
and
no,
they do,
okay, sorry.
And so when they study the Bergman projection, when gamma is for every gamma, and if gamma is rational, they do have an interval where the Bergman projection is bounded. When gamma is irrational, there is no way that the Bergman projection is bounded. It's only bounded on p equal 2.
So it was not them that they studied the weighted case.
No. Chen, for instance, Chen studied sorry. Chen and
only the power of
Chen
Z2.
studied only this power here.
In that case, what was the regularity in that P?
I mean, the situation changes a lot whenever, but he always found, he's pretty much always found an interval which depends on where the projection is bounded or not. But he works on the triangle, and he consider, on the classical triangle, he consider weighted Bergman projection. So his domain is really my domain, let's say.
Yeah.
And the difference with me is that I have some extra factors in my weight, and I mean, the way he proves the Bergman project, the boundedness of the Bergman projection is equal, or I mean, we prove the boundedness of the Bergman projection in the same way. My interest was to find actually a family of spaces with spaces that are not only Bergman spaces. So I have some extra factors, and I define some different spaces which are not Bergman spaces.
No, but also yours are they have some invariance with respect to the your weight is well behaved where it's conformally.
Yeah, sure.
Taking the powers of the Jacobian, yes.
Exactly. Yeah. And then about the fact that, for instance, you asked that, I mean, the Ziggo projection is bounded for any p. That's true, and it's also true that where is it? because sorry, no, the weighted Bergman. Okay, sorry. So this is the result for the weighted Bergman projection. And my case is when the RD space is when nu goes to -1.
Okay.
But if you take -1, when you take, I mean, if you take the limit for nu that goes to -1 in this interval, you do not obtain one in the interval 1 plus infinity. So we really have a different behavior. And I think that this might due to the fact that if you take the kernel, where is the kernel? These are my kernels here. Mm-hmm. That in the weighted Bergman case, you always have an extra factor here somehow. This factor here. Whereas when you consider the nu equals -1, sorry. Here you lose a factor at the origin somehow. The things cancel out and you have more regularity. So I mean, at least this is an indication, of course, of the computation and of the fact that why the things goes better. A deeper reason, actually, I think that in the end, my RD spaces is modeled on the distinguished boundary of the domain. Because I wanted this kernel, a defined space, and actually this space is completely defined, and somehow it only depends on the distinguished boundary of the domain, which is the torus. So we completely lose somehow the fact that we have a pathological point here at the origin. So maybe that's another reason that we lose sight of the origin somehow now in the definition of my space.
Okay.
Because also here we identify my space with a subspace with a subspace of the distinguished boundary, because as Nicola was saying, what are the boundary values at the origin? I mean that's a problematic point.
But the origin measures 0 with respect to
that's also a problem how to define the Hardy spaces. Yeah, it has measure 0, but somehow you lose the fact that there you have a problem for this reason, probably because it has measure 0 and you end up only working on the distinguished boundary.
Okay, thank you.
No, thank you.
Are other questions? Well, then we thank Alessandro again for the very nice talk.